predicting reactions for or predicting products for these reactions a little bit. And because of the rain out, we were only able to cover three of the five. I think after we've done it, you're happy we only had to do three and not all five. So here are the three I picked. First one is synthesis. So things coming together, right? We talked about how sugar and eggs and flour and vanilla and butter and all these things become one cake. So when you have only a plus on the reactant side to become one thing, one compound, that is considered synthesis. So there's only one compound on the product side. The addition of things comes on the reactant side. So we have to be able to predict what these things are going to make. And that has to do with their charges. Remember this? It's coming back. All right. So magnesium. Magnesium in each case, the +2 charge. All right. So this has a +2 charge and this has a +2 charge. Chlorine, when it's in an ionic compound, has a -1 charge. So each one of these wants to be -1. So when Mg comes together with Cl, that +2 needs two -1s to neutralize its charge to 0. And so we represent that as MgCl2. So Mg plus Cl2 makes MgCl2. With oxygen, oxygen is a diatomic, O2, but when it's in a compound, oxygen has a -2 charge. So if Mg is going to get together with oxygen, it only needs one of each. So that's going to form MgO. All right. Potassium has a +1 charge. Sulfur over here has a -2 charge. So if we're going to have those two come together, a potassium plus a sulfur, we're going to need two potassiums, and that's K2S. Two potassiums, one sulfur. Sodium is the same thing. It's a +1. Right? It's going to get together with oxygen, which is still -2. Just like with up there, sodium +1, oxygen -2. We need two sodiums to neutralize that charge and give us Na2O. So being able to figure out these products has to do with balancing the charges here. Once you've established what the products are, you can then balance the equation. So since there's two oxygens, I needed two magnesiums. Since there's two potassiums and K2S, I needed two potassiums. Since there's O2 for the oxygen, I needed four sodiums. So therefore, I needed two Na2O. But that's how we do that. And that's synthesis. So now what we're going to do is look at some um, single replacement. So single replacement reactions involve where something is alone and it switches places with something that's in a compound. So here we have something that's lonely, and here we have something that's lonely, and the lonely thing changes, right? It went from iron to copper, and then you can see that here. Here's the iron kicking out the copper. All right, so for these things, we're going to want to switch those metals around. So the zinc will be by itself, and the sodium is going to be in a compound. But now we need to manipulate the charges still. Sodium, according to our chart, the +1. So sodium has that +1. This sulfate is a polyatomic ion. So we've given you the polyatomic ion list right here, and sulfate on that list tells you it's -2. So if sulfate is -2, it needs two sodiums to neutralize that charge. And that's why we have Na2SO4. All right, and then we balance it. So if we have two sodiums, we needed a two here. All right, so here are some examples. This is the activity series. This is also available on that chart that we gave you. So the activity series is right here, and it's very useful for explaining things. For example, everything on the bottom, this is what we make our jewelry out of. We have silver, platinum, and gold. These like to be alone, and they don't react. Okay, and that's why you can wash your hands or work on the car or clean the dishes, and your rings and stuff made out of good jewelry won't dissolve. The things up top actually like to lose electrons and become ions. That's why we have lithium batteries, because they love to lose electrons. And remember, we talked about how electrons moving is what electricity is. So if potassium, which is up here, and iron, will they switch places? Yes. Iron prefers to be alone. It's closer to the alone thing. Potassium is closer to the wants to be together thing, wants to lose electrons. So these will switch places. And potassium will get together with the OH, and iron will be by itself. Now we need to make sure the charges on this are all straight. So we got to go to potassium, +1, and we have to go to our polyatomic list, and hydroxide is -1. So that's a 1-to-1 situation. So that is good, and iron by itself is good. If we want to balance that, there's two oxygens here. So we need a 2, and then that gives us two potassiums. So we need a 2 there. All right, so calcium and um, silver. Silver's down here. It likes to be alone. It is not alone. It's with a couple. Calcium is up here. Calcium likes to have a person with a likes to be in a compound. It's currently alone. So they're going to switch places. So the silver will be by itself, and the calcium will want to be with that nitrate. So I bring that whole nitrate together because it's a polyatomic. It's a polyatomic because it's on this list. Nitrate is on this list. So we bring the whole thing together, and it has a -1 charge. So if the nitrate has a -1 charge, and each calcium has a +2 charge, that's true here. Did we do that one? Nope, we didn't. There's calcium, +2. So +2 needs two -1s. So we need two nitrates to balance out that calcium. But we need the whole nitrate twice. All right. So then again, balancing wise, there's two N's here. There's only one here. So we need a 2. There's 6 oxygens here. Now there's 6 oxygens here. That's balanced. One silver, up, two silvers here, two silvers there, one calcium. All right. For this next one, we're looking at gold. All right, and gold is down here, or silver again, I guess. Silver, I'm sorry. We're looking at silver again. And this time it's going to want to kick out a potassium from a compound. Well, potassium likes to be with a compound. It's happy up there, and silver likes to be alone. So we say no reaction will occur because silver is where it wants to be alone, and potassium's where it wants to be with a partner. This next one, though, that's going to have something going on. So let's take a look at zinc and magnesium. So zinc is closer to the alone side, so it will like to be alone. And magnesium's closer to the wants to be with something side, so it's going to want to be with the chloride. So let's check out our charges. Zinc is always +2. Magnesium is also +2. Well, that's nice. They're both the same charge. Chlorine is -1. So if zinc's +2 and magnesium's +2, and each one of these is -1, that's why zinc needed two chlorines. So then when magnesium's with chlorine, it's going to need two so that its +2 neutralizes to 0. And balancing, we don't need to do any balancing for that one. All right. So that's when we're replacing a metal with another metal. Sometimes we're going to have to replace a metal with water. Those are the metals up here in this box because look right here. It tells you replaces hydrogen from cold water. So water is H2O, which is another way of looking at that is a hydrogen with an OH, right? H2, two hydrogens and an oxygen. That first hydrogen is going to be what switches places with the metal. So the switching is going to happen right there, just like before. So is sodium in this box? Yes, sodium's in that box. So sodium is going to get with the OH, and we're going to form H2, as we say here, with when hydrogen goes off by itself. So this hydrogen that goes off by itself needs a partner. It's a diatomic. It likes H2. Sodium's charge is +1. Okay. And we can even say hydrogen's charge is +1. It's right there. Hydroxide, the OH, is in here. Hydroxide is going to be -1 every time for all of these. So if we have the -1 hydroxide and the +1 sodium, those neutralize. That's good. And we have the H2. So that's what that's going to form when that gets thrown into water. And so then we saw this video, I'm pretty sure, real quick. Um, so we saw this video, well, not this one, but here's sodium getting thrown into a river. But there's the sodium. And when they throw that chunk of sodium into a lake, let's go throw it into the lake. So much. All right, so there it goes. There's the sodium right there. And as it falls into the lake, it reacts with the water in the lake. It exchanges the sodium for the hydrogen. And the explosion you see is a result of the hydrogen gas that's produced catching on fire by all the heat that's released by that reaction. All right. So that's what we're talking about with reacting with water. All right. So calcium, calcium as a metal is not what we have in milk. That's calcium 2 plus. And the reason that happens is because calcium likes to change places with hydrogen and water. So the calcium gets together with the hydroxide and then it releases hydrogen gas. So the calcium that you have in milk is already the +2. You already have calcium +2 in milk. So calcium's +2. We know that because it's on this thing right here. Calcium is +2. It's becoming quite a mess, but okay. All right. Hydroxide's always -1. So to neutralize that charge, we need two hydroxides to get that to 0 and H2. And then if we were going to balance this, that's two oxygens. There's only one oxygen here. So we'd want to put a 2 there. And then that gives us a total of 4 hydrogens, 2, 4. So that's all good. So will silver react with water? No, silver's down here. Water's up there. It's not in that blue box. So this is going to be no reaction. And that, again, is why we wear silver jewelry because you can wash your hands and it won't catch on fire. Acids have the same situation, only look how much space the acids take. There's a lot more acids. There's a lot more metals that'll react with acids. All of those metals are going to react with acids. Will gold react with those acids? No. Gold, right? Gold is down here. This is going to be no reaction. But let's do the other ones. So it's going to be just like what we were doing. The zinc is going to replace the H, and it's going to form H2. Zinc has a charge of +2. Chlorine has a charge of -1. To neutralize, we need two chlorines. And again, we're getting that from sheet here. Chlorine's -1, zinc is +2. All right, so I'm going to stop going to that so you don't get car sick. Magnesium is going to switch out with the hydrogen, right? So magnesium's in that box, zinc's in that box, calcium Calcium's in that box. So magnesium's going to switch with hydrogen as well. Magnesium's +2, each chlorine is -1, so we need 2 of them to make that happen. Okay, so then balancing wise, these will have the same balancing. You need 2 of these to provide the 2 chlorines, and then 2 of these also to provide the 2 hydrogens. Calcium is also +2. +2. Nitrate is -1. That is on this thing. Nitrate is here. That's on this thing. So nitrate's -1. Calcium is +2. So when those come together, it needs 2 nitrates to counterbalance its +2. It needs 2 -1s, and it's also going to make H2 gas. So that's the +2 of that, and then 2 -1s to give you 0 as a neutral compound. All right, so those are the single replacements. You need to know when it's with an acid, it's going to be only those that are in the red box. When it's with water, it's going to be only that smaller group in that blue box. And when it's with another metal, it needs to be higher up if it's going to be in the compound. Okay, so if silver is in the compound, it'll get kicked out and be alone because things down here like to be alone when the reaction's done. And things up here like to be with in compounds. Then we talked about these easy ones, combustions. Anytime you have a carbon hydrogen thing, remember your combustion reactions. Hold on again. These are your combustion reactions. The general form of some carbon hydrogen thing plus oxygen makes carbon dioxide and water. So the beautiful thing about those are when we're predicting products, we just make carbon dioxide and water every time. So that's not hard. The harder part with these is the balancing. So balancing, all of these are always going to have CHO. The carbon all goes to the carbon dioxide, so that's 1 and 1. The hydrogen's all going to go to the water. So currently we have 4 on this side. There's only 2 hydrogens on this side, so we need to multiply that by 2. 2 times 2 is 4. That's 4 hydrogens on that side. Oxygens go to 2 places, so that's where it gets a little confusing, because oxygen goes to both products. And because it goes to both products, there's 2 plus 2 is 4. So we need 2 of these. 2 O2s to give us 4. All right, so balancing these, there's 3, there's 1, so we need 3, so we get 3 of each side. There's 8. They all go here, so we need a 4 there. 4 times 2 is 8. So that's good. Our oxygens, 3 times 2 is 6, plus 4 is a total of 10. We all get the oxygens from here, so if there's 10 on that side, we need 5 O2s to make 10 on that side. And so this last one, C4, they all go here. So we need 4 carbon dioxides. H10, they're all here. So we need 5 waters to get 10 hydrogens. Then oxygen-wise, 4 times 2 is 8, plus 5 is 13. This side has 13. 4 times 2 is 8 oxygens, plus the 5 is 13. There's 1 oxygen here. So that means we need 12 to come from here because we have a total of 13. So since 1 is here, 13 minus 1 is 12. We would want 6 of those to give us a total of 13 on that side.